Welcome to Unit 7. We have moved concavity to Unit 6, so Unit 7 will just be L'Hopital's rule, graphing, and optimization. Congratulations on making this far. This is the last unit for all of Calculus 1. After this unit, Unit 8, which we'll do after the first of the year, we're moving into Calculus 2, antiderivatives, and integrals. So excellent work making it all the way through Calculus 1. Before we start talking about L'Hopital's rule, first we need to talk about indeterminate forms. So this word indeterminate is when we can't figure out the limit of something. It happens when we have 0 over 0, infinity over infinity, 1 to the infinity, 0 to the infinity, infinity to 0, 0 times infinity, or 0 infinity minus infinity. The two that we're going to be focused mostly on when we talk about indeterminate forms are 0 over 0 or infinity over infinity. And when we have those, we get to use L'Hopital's rule, which is super cool and really exciting. It says that if you have the limit of two functions as x goes to c, and we know all the way from back in Unit 1, that's the limit as x goes to c of f of x divided by the limit as x goes to c of g of x. Now, using what we know now, we don't know how to solve that. So if I have the limit as x goes to c of f of x equals 0, and the limit as x goes to c of g of x also equals 0, I'm going to get this indeterminate form of 0 over 0. L'Hopital's rule helps us tackle those exact indeterminate forms. So let's read the rule. Suppose the function f and g are differentiable in the open interval I containing a number c, except possibly at c. If g prime of x does not equal 0 for all x in c, let L denote either a real number plus or minus infinity, and suppose f of x over g of x is an indeterminate form of c of the type 0 over 0 or infinity over infinity. That was a lot of words. And what really is important there is that we're going to get this indeterminate form from our limit. What's super cool about that is we get to take the derivative of the numerator over the derivative of the denominator. This only works for these indeterminate forms, and this is how we're able to find the limit. So let's do a couple of them, and I think that they'll start to make some sense. So before we use L'Hopital's rule, we have to make sure that we get this indeterminate form of 0 over 0 or infinity over infinity. If we don't have 0 over 0 or infinity over infinity, we don't get to use L'Hopital's rule. Then we differentiate f and g separately. Then we find the limit as x goes to c of the derivative, and this limit is equal to the limit as x goes to c of f of x over g of x. And if we get f prime over g prime is another indeterminate form, we just keep going. So again, like I said, let's do a couple examples, and I think this will really make sense. So the first thing I'm going to do is evaluate the limit of the numerator and the limit of the denominator separately. So my limit as x goes to 0 of tan x. You can look back at unit circle, you can look it up, but that's going to be 0. Then I'll take the limit as x goes to 0 of 6x, which is also 0. So since I'm going to get an indeterminate form of 0 over 0, I get to use L'Hopital's rule. Now, I want to make this really clear. You do not ever, ever, ever write equals 0 over 0. You will always get a point taken off the AP test for this. This is not allowed. 0 over 0 is not how you write that. You have to evaluate the limit separately. Because 0 over 0 is an indeterminate form, that's like writing something that doesn't exist. So you're not allowed to write that something equals does not exist. Okay, so now let's take L'Hopital's rule. L'Hopital's rule tells us that I can take the derivative of the numerator. So my f prime of x, the derivative of tangent is secant squared x, and the derivative of the denominator. The derivative of 6x is just 6. So now I have the limit as x goes to 0 of f prime of x over g prime of x. So the limit as x goes to 0 of secant squared x over 6. Now, if you're not sure about what secant squared is, let's take a minute and take a step back and talk about it. Secant is 1 over cosine, So let's evaluate that. The limit as x goes to 0 of 1 over cosine of 0 squared. Cosine of 0 is 1, so we're going to get 1 over 1 squared, or just 1. And the limit as x goes to 0 of 6 is just 6. So this is going to become 1/6. That means my limit overall, the limit as x goes to 0 of tan x over 6x, is also 1/6. This is really powerful because we just did a lot of shortcuts that didn't involve graphing, making a table, or doing any other fancy factoring or other multiplication tricks. Let's take a look at another example 3 on page 333. First thing we do is evaluate it separately. The limit as x goes to 0 of sine x minus x. So sine of 0 is 0, minus 0 is still 0. And then I take the limit as x goes to 0 of x squared. That's going to be 0 squared, or 0. So I'm going to get this indeterminate form, so I use L'Hopital's rule. It tells me to take the derivative of the numerator. The derivative of sine is cosine x. The derivative of x is 1. And then the derivative of the denominator, which is 2x. And now I'm going to take the limit as x goes to 0 of each of these. Now hopefully remember that the cosine of 0 is 1. So we have 1 minus 1, or 0 there. And again, we get the limit as x goes to 0 of 2x, which is 2 times 0, or 0. Since I'm going to get another indeterminate form of 0 over 0, I get to use L'Hopital's rule a second time. So let's take the next derivative. So the derivative of cosine is negative sine x, the derivative of 1 is 0, and the derivative of 2x is 2. And now I repeat the same process. I take the limit as x goes to 0 of both of these. Sine of 0 is 0, and negative 0 is still 0. But now my derivative for my denominator is just 2. So the limit as x goes to 2 of 2. So I get 0 over 2 as my limit, which is just 0. So just by using a couple of quick derivatives, I'm able to easily and quickly come up with the limit as x goes to 0 of this kind of complicated function. On example 4, we're going to take the limit as x goes to infinity. It's the exact same process, but we're going to get a slightly different outcome. Instead of having zeros, we might have infinities. So we do the same thing. The limit as x goes to infinity of ln x, the natural log of infinity is still infinity, and the limit as x goes to 0, to infinity of x is still infinity. So now I get the indeterminate form of infinity over infinity. So we get to use L'Hopital's rule. And I'll take the derivative of the numerator is 1 over x, and then the limit as x goes to infinity of 1 over x is 0. I'll take the derivative of the denominator, which is x, and the derivative is just 1. And the limit as x goes to infinity of 1 is still just 1. So this is going to be 1 over 0, 0 over 1, or just 0. Let's take a look at part B. Same process. I take the limit as x goes to infinity of x, which is infinity, and the limit as x goes to infinity of e to the x, which is also infinity. Since I have my indeterminate form of infinity over infinity, I use L'Hopital's rule, and I take the derivative of the numerator, which is 1, and the derivative of the denominator, which is e to the x. So now I'll take my limit as x goes to infinity of 1 is 1, and the limit as x goes to infinity of e to the x is infinity. So my derivative is going to be 1 over infinity. So that's, I have $1 and a million people who need money. Everyone gets basically no money. All right, let's see the inverse of that. So we'll have the limit as x goes to e to the x is going to be infinity, and then the limit as x goes to infinity of x is also infinity. So I get to use L'Hopital's rule again. And we did this in the previous problem, but we'll keep going. The derivative of the numerator is e to the x, and the limit as x goes to infinity of e to the x is infinity. And then the derivative of the denominator is 1, and the limit as x goes to infinity of 1 is just 1. So now I have infinity divided by 1, or just infinity. So in example 4, we get this really nice rule. If we have the natural log of x over x to any power, my limit is always going to be 0 as I take x into infinity. And the same thing if I have x to the n over e to the x. As x goes to infinity, my limit will always be 0. You can, of course, you don't have to memorize this rule or anything. You can always actually just derive it as we did in the previous slide. Let's take a look at example 6 on page 335. It asks us to take the limit as x goes to 0 of cotangent x over natural log of x. So we're going to do the same thing as we've done before and evaluate the limit from each direction. So we'll look at the limit as x goes to 0 of cotangent x, and then we'll look at the limit as x goes to 0 from the right of natural log of x. Now you might not remember at all what cotangent of x looks like, so it might be useful to just throw it in your graphing calculator. And I get a picture that looks a lot like this. So I'm looking at as x goes to 0 from the right, what happens to my y values? They look like they go to positive infinity. And then same thing for natural log of x. I'm not sure that you know what it looks like, so you really might want to graph it. It's going to look like this. And it kind of drops off on your picture, but if you keep tracing, you'll see that as you go to 0 from the right, it goes to negative infinity. Now, since infinity over negative infinity, or infinity over infinity, is an indeterminate form, we get to use L'Hopital's rule, and we'll take the derivative of the numerator over the derivative of the denominator. So the derivative of cotangent is negative cosecant squared x, and the derivative of the denominator is 1 over x. Now let's take a minute and resimplify our equation. We're going to have the limit as x goes to 0 from the right of negative cosecant x squared over 1 over x. I can rewrite this as the limit as x goes to 0 from the right of negative 1 over sine squared x over 1 over x. And I get to rewrite this, the limit as x goes to 0 from the right. If you're not sure about how I'm doing this, it's really important that you go back and try it yourself using the fraction division rules. Now this looks a lot easier and less intimidating to take the derivative of. So let's take the derivative of the numerator and the derivative of the denominator and see where we stand. So let's plug in the limit as x goes to 0 from the right of negative x. I'm going to be getting 0 there. And then we'll plug in the limit as x goes to 0 from the right of the denominator. The sign of 0 is 0. So 0 squared is still 0. Now we get another indeterminate form. Now recall, my numerator was x, so my derivative is going to be just 1. My denominator was sine squared x. So let's rewrite that as sine x squared. And then the derivative of my denominator is 2 sine x times cosine x. Don't forget your chain rule there. Now we'll take the limit as x goes to 0 from the right of 1 over, oh, I forgot my negative sign, negative 1 over 2 sine x cosine x. Now let's break this up. I know that this is the limit as x goes to 0 of negative 1/2 times the limit as x goes to 0 from the right of 1 over sine x times the limit as x goes to 0 of 1 over cosine x. So the limit as x goes to 0 of negative 1/2, that's not too bad. I can multiply that. It's negative 1/2. and the limit as x goes to 0 of 1 over cosine x is just 1. However, this inside term is a little bit more complicated. We're going to have to look back to our squeeze theorem that we did a long time ago back in Unit 1 or Unit 2. And we know, if we look back at the squeeze theorem, that the limit as x goes to 0 of 1 over x is actually going to be infinity. So it's negative 1/2 times infinity times 1. So we're going to get a negative infinity for this equation. So to summarize the indeterminate forms and using L'Hopital's rule, we get to use L'Hopital's rule whenever we have 0 over 0 or infinity over infinity. When we get the other indeterminate forms, we're going to need to rewrite them as 0 over 0 or infinity over infinity before we can use L'Hopital's rule. Example 7 on page 335 is showing exactly this. We're looking at the limit as x goes to 0 of x times ln x. And when I evaluate this separately, the limit as x goes to 0 from the right of x is 0. And then the limit as x goes to 0 from the right of ln x is going to be negative infinity. Now, while this is an indeterminate form, it's not one that I can use L'Hopital's rule for. So I'm going to do a little bit of fancy arithmetic here and say multiplying by x is the same as dividing by 1 over x. So I'm going to rewrite that as ln x over 1 over x. Now, while these are equivalent, the second form helps me be able to use L'Hopital's rule, because now I have an indeterminate form of infinity over infinity. So we can take the derivative of the numerator, which is 1 over x, and the derivative of the denominator is negative 1 over x squared. So let's simplify that, and I'm going to get the limit as x goes to 0 from the right of negative x squared over x, or the limit as x goes to 0 from the right of negative x, which is going to be negative 0, or just 0. And for the part B, the limit as x goes to infinity of x sine 1 over x, it's going to be a very similar process. First, we'll take the limit of each piece, so the limit as x goes to infinity of x times the limit as x goes to infinity of sine 1 over x. So we have infinity times sine of 1 over x. Again, we use the squeeze theorem for that, and we're going to get 0. And while this is an indeterminate form, it's not very helpful for using L'Hopital's rule. So we're going to simplify again and do some fancy arithmetic, again by dividing by 1 over x. So the limit as x goes to 0 of sine 1 over x divided by 1 over x is equivalent, so I know it's going to be my indeterminate form, but now I have it as 0 over 0. So let's take the derivative of the numerator and then the derivative of the denominator. So we'll get the limit as x goes to infinity. The derivative of sine is cosine 1 over x, and the derivative of 1 over x is negative 1 over x squared divided by negative 1 over x squared. So since I have the same thing in my numerator and my denominator, those two pieces are going to cancel each other out. So those will cancel. And my whole form just becomes the limit as x goes to infinity of cosine of 1 over x. If you're unsure about this, you're welcome to graph it, and you'll see that this equals just 1. When we have the indeterminate forms of 1 to infinity, 0 to 0, or infinity to 0, we're going to have to do a little bit of fancy footwork here to figure out how to get those into an indeterminate form that we can use. So the first thing we're going to do is take the natural log of both sides. I know we've been working with some natural logs since related rate problems, and these natural log rules are really, really useful. What happens when I take the natural log of both sides, or the log, the exponent comes out in front. So that's why it's ln y times g of x ln f of x. Now I can find the limit as x goes to c of ln y, and then I know on the other side of my equation that will be the same as e to the l. So that limit, I'm going to have to put it back in to my original and undo the taking the natural log. Let's do an example of this to make it a little bit more concrete. So if I have the limit as x goes to 0 from the right of x to the x, I'm going to first set my equation to y equals x to the x. Now I'll take the natural log of both sides. The natural log equals the natural log of x to the x. And since I'm taking the natural log of something with an exponent, that x gets to come out in front. So now my equation's the natural log of y equals x times the natural log of x. Now we'll take the limit as x goes to 0 from the right of both sides. And I know that the natural log of 0 is going to be 0. So this whole piece is going to equal 0. Now, of course, I know that the limit as x goes to 0 from the right of ln y is 0, but that's not what my equation asked me. It didn't ask me for the natural log of y. It wanted to know just y. So in order to undo this, I need to take the exponential form of each piece. So to undo natural log, I take the e to both sides. This will undo this side, and I get just y. And e to the 0 is 1. So that means that my limit as x goes to 0 from the right of x to the x is 1.